Alright, this is going to be a video editorial for Codeforces round 895, division 3, contest ID 1872. So these are some solutions that I came up with on the last problem. I took some inspiration from the editorial, the Codeforces editorial, and some of the comments in the contest announcement. Just a quick disclaimer that some of these solutions might not be the most optimal solutions, but I think all of them are quite intuitive, or as intuitive as can be. So this document over here is just going to be some notes as I walk through the solutions, and I will also show each of my implementations. And all of my implementations will be linked as Codeforces submissions in the description. This notes document will also be in the description. So we start off with problem A. Quite simple. I'm also going to kind of gloss over the problem statements and assume that anyone watching this has read the problem. So the key thing in this problem is the difference between the two vessels, and every unit of water we move from one to the other decreases the difference by 2 units. So if we have like 3 units of water in this one and 10 units of water in this one, if we move one over, then we have 4, obviously not to scale, and 9, so the difference went from 7 to 5, obviously, with basic math. So we can move C units at a time, and we need to decrease the difference to 0. So on each move we can decrease the difference by 2C. We need to round up at the end. So a trick we can do is, if we need to do A over B and round up, we can do this, assuming everything's integers. So this is my code for that problem. If they're equal, we don't have to do anything. We take the difference and round up. I did some even odd case, but this is not necessary. Actually, a better implementation that I have is right here. So take the difference, round up, output. Simple. Go to problem B. So for problem A, we can do this in constant time, just one quick subtraction and division, and we're done, no matter what the numbers are. So we go to problem B, and the concept in problem B is when we run over a trap, we need to get back in time before the trap triggers, but we want to go as far as possible. So I'm going to call the distance we go past a certain trap as k. So let's say these are all the rooms, and then say this is a trap, and let's say we want to go here, so this would be our k. So let's say this has a 4-second delay. We cannot actually make it to this room and back, since we would go 1, 2, 3, 4, and then it would trigger as we get there, and then we wouldn't be able to get past it. So it takes us, so this is k equals 2, and it takes us 4 seconds to get back. And this is a 4-second delay. So the time we need to get back is 2k, since we need 2 seconds to get to 2 rooms ahead, and then 2 seconds to get back, has to be less than the delay. Now, if SI is even, then k can be SI over 2 minus 1. So in this case, delay is 4. SI is the delay. SI is 4. 4 over 2 minus 1 equals 1. So that means we can get to this room here, but we can't get to this room. Now let's say SI was even, so let's say this was 5 seconds, we would actually be able to get to this one because we'd take 1, 2, and 3, 4, and we would get back in time, and then the trap would trigger when we were in this room on the way back. So if SI is odd, K can be S minus 1 divided by 2, so 5 minus 1 over 2 is 2. So I'll go into the math for this, but you can rearrange this such that you can generalize it to all cases, so you don't have to do this even odd case as this one, the odd case. So for every trap, we can go as far as x, or its location, I think in the problem is d of I. So we can go d of I plus k. So we can compute this for each trap furthest we can go. And then we will pick the minimum. Since if one trap only allows us to go to room 10, it doesn't matter if every other trap allows us to go to room 20. We need to get past all the traps on the way back, so we can only go to room 10. So we simply iterate over all the traps and find the one with the smallest range. So this is the generalized K, formula for K. Find the range of this trap. If the range is more restrictive than what we have so far, update it, output it at the end. Quite simple. Linear time, since we need to make this simple computation for each trap. Alright, moving on to problem C. Non-prime co-split. So essentially we need to find two numbers whose sum is within the given interval and are not coprime. So they have some GCD that's not 1. So let's make the observation that the GCD between 2 and any even number is 2. That's quite obvious, since 2 divides 2 and 2 also divides any even number. I should say this is at least 2. At least 2, and this is greater than 1. And therefore not equal to 1. So if there is any even number in our interval, we can just take it and use it. Now the reason why I say other than 2 is because if 2 is in our interval, we can't use 0 and 2, since a and b have to be positive. So my code for this one, let's make the first observation that if r is less than 4, we can't do anything. Since 1, the only way to break down 1 is to 0 and 1. 0 is not positive. For 2, we can break it down to 1 and 1, but the GCD of 1 and 1 is 1, so it doesn't work. And then 0 and 2, 0 is non-positive. For 3, we can break it down to 0 and 3, 0 is not positive. 1 and 2, GCD is 1, doesn't work. So if r is 4, we can't do anything, so we just fail immediately. Now, if r is even, that means there's an even number in the interval, since the endpoints are included in the interval. So we just simply take 2 and r minus 2 as discussed up here. So that's easy. If r is odd, but L is less than R, which means that the interval is length at least 2, this means R minus 1 is even and it is located in the interval, since L is less than R. So that means R minus 1 is within the interval. So we can use 2 and R minus 3. So we can use R minus 1 as our sum, which is even, and then we can take 2 and R minus 3 as our numbers. So a good example of that is R here is odd, but L is less than R, so that means 14 is available. So we can just take 2 and 12 equals 14, and 2 and 12 have GCD too. Now the tricky part is if R is odd and L is greater than R, or L is equal to R. So we only have one number, so this is an example of that. L and R are the same, R is odd. So there's no even numbers available in here. So if that happens, we do this basic primality check where we iterate over every odd number starting at 3 up to the square root of R to check divisibility. So we check 3, check 5, check 7, and eventually, if R is not prime, we'll find some divisor, and we can take D and D minus R. Those will equal, together those equal, or it should be R minus D, I should say. R minus D, and their GCD will be D, which is greater than 1, since we started with 3 as our first divisor check. And they'll sum up to R, which is in this interval. So if this check completes without us finding a divisor, that means that R is prime, and there's no solution. There's no solution because R has a GCD with every number of only 1 except itself. And except itself or some multiple of itself. And if it's with itself, the sum would be R plus R is 2R outside the interval, and same with any multiple, it would just be outside our interval. So that would be invalid, and we don't have an answer. So we fail here at the end. So the time for this one is up to square root R. That's for this primality check. If we end up in this case, it is runtime square root R. If L equals R and R is odd. Otherwise, if we end up in any of these earlier cases, we can do this in constant time very quickly. Constant space, since we don't need to, we only need to store the endpoints of the interval. Alright, moving on to question D, plus minus permutation. So, concept behind this one is pretty simple, so I'll give an example array. Let's say we have 3, 5, 2, 4, 1, 6. So I'll use one indexing for this problem. So this index, let's say, so n equals 6, x equals 2, y equals 3. So I'll do this. So the red indices are multiples of 2, and the blue indices are multiple of 3. So clearly we want to put our biggest numbers in the red boxes and the smallest numbers in the blue boxes, since the red numbers count as positive, the blue ones count as negative. Now for the boxes that have both red and blue, whichever number is in here, so in this case 6, it won't affect our score at all. So our score would be 5 plus 4 plus 6 minus 2 minus 6. So these would cancel out. So in that sense, any number that's in here is the same as a number as like this number. This number and this number both don't contribute anything to our score, positive or negative. So we want to take, there's some number of red boxes, of only red boxes, and some number of only blue boxes. And let's call the number of red boxes S, and the number of blue boxes as T. So we want the S biggest numbers and the T smallest in order to maximize our score. So we want to figure out the number of indices that are only red and the number of indices that are only blue. So we can do that with some simple division. So first we find boxes that are red, all boxes that are red, even ones that are both. So 6 over 2, 3 red boxes, 6 over 3, 2 red boxes. But the problem is both of these numbers include the overlap. So in order to find the overlap, we take the LCM, least common multiple of x and y. So LCM 2 and 3, that equals 6. So any multiple of 6, 6, 12, 18, so on and so forth, these are red and blue. But we want to ignore these boxes since they have essentially the same effect as boxes with no color. So we take n over LCM, so that's 6, so n over 6, one box that's both colored. So we only have 2 boxes that are only red and 1 box that's only blue. So we want to find the 2 biggest numbers and put them in our red spots, and our 1 smallest number and put them in our blue spot. So we take the s biggest numbers, obviously the biggest number is n, next is n minus 1, and so on. So in this case we would take 6 and 5 to put in our red spots, and then the t smallest number, so t is 1 in this case, obviously the smallest number is 1, so we would just take 1 to put in our blue box. So then our answer would be 6 plus 5 minus 1 equals 10. So this is our maximum score, which we would output. We don't actually have to construct this permutation. In fact, we don't have time for that, the time or the space for that, since n can be up to 10 to the 9. 1 second, we have 1 second, that's about enough for 10 to the 7 operations. We have 256 megabytes. An array of the size of 10 to the 9 would be about 8 gigabytes. So we don't have enough space or time for that. Of course, that's not necessary. So in order to compute the in order to compute these sums, we can take, so if we had like, let's just say s was 3 and t was 2, we would take 6 plus 5 plus 4 and then 1 plus 2. So using the Gaussian sum, which is like this, the sum of all the numbers from 1 to I are, from 1 to n is this. For the s biggest numbers, we're essentially taking 6 plus 5 plus 4 plus 3 plus 2 plus 1, but without this. So we can just do Gauss of 6 minus Gauss of 3. Right? Because then we can just do this. And then for this one, we can just do Gauss 2. So generalized in terms of s and t, that would be Gauss n minus Gauss n minus s, and this would be Gauss t. So our answer, and since the t smallest numbers count as negative, we would do this. So our answer equals Gauss n minus Gauss n minus s plus, or minus Gauss t. So in my code here, I have I just have helper functions for GCD and LCM and Gauss. I get the number of x indices and y indices. So this is only red, only blue, say red and all red and all reds, all blues, reds and blues. or boxes that are red and blue. So then this is S biggest numbers, T smallest numbers. Then we simply do this. That's what the last line of the code does here, and then we're done. So this takes log n time, since our helper functions of GCD or LCM, which I use GCD to implement, takes log n time, and we don't need to store anything, so constant space. Next question, data structures fan. So essentially every number is either marked by 0 or 1. So if it's marked by 0, I'm going to put it in set A, and if it's marked by a 1, I'm going to put it in set B. So each element can only be in one of these two sets, but it's in exactly one of them, not 0, not 2. So I'm also going to call the XOR of all the numbers in A XOR A, and all the numbers in B XOR B. So essentially we just need to keep track of a running XOR sum of XOR A and XOR B. And if we get a 2 query, we just report our running sums that we have right now. If we have a 1, then we just need to update them. So when we get a query LR, an interval, we're essentially, so I think the example they gave us is this. So this is set A, this is set B. So right now in this set there's a 2 and a 3, and this is 1, 6. So XOR A equals 1, XOR B equals 7. So I think the query they give is this. So that will toggle these bits. So essentially we need to remove, so these would swap over, and then this number would swap over. Now the key insight is that both you can add or remove a number from an XOR set by XORing it. So if I want to remove 2 from here, I would just do 1 XOR 2 and I would get 3. If I want to remove 3 from the set after that, so remove 2, this becomes 3, and if I wanted to remove 3, then I would XOR 3 with 3 and get and then I would get 0. And then to add them to this, I would XOR 7 with 2, I would get 5, and then I would XOR with 3, and then I would get 6. So then I would have to add 1 to A, so I would add 1, 0 XOR 1 is 1, and then I would XOR 6 with 1, and then I would get 7. So from this specific operation, the numbers ended up not changing, but you'll see how the update can be done. Since XORing a number, if it's in there, is essentially removal, and if it's not in there, it's essentially adding it. That's the logic behind our updates. So the naive thing to do at this point would be like what I shown in this picture. For A, I add all the elements that weren't there, and then I subtract all the ones that were. For B, I add all the elements that were not there and subtract all the ones that were. The problem is that this interval could be on the order of n elements long, of n indices long. And we could have O of n of these queries. So that means our runtime would be O of n squared, which is too slow, because we only have 2 seconds, and n can be up to 200k. So what we can do is we can take a prefix XOR of the whole array. And what that allows us to do is immediately update our XOR sum. So let's say this is our array. And let's say we get a query LR. So we essentially want to do, let's call the XOR of these three elements together Y. So we essentially want to do this. XOR A equals XOR A XOR Y. And the same with B. So XOR B equals XOR B plus equals Y. So XOR Y. So we need to find Y quickly, basically. That was the problem with our old approach. If we found it by doing this element XOR this element XOR this element, that would be too slow. With the prefix, we can do two quick XOR calculations and instantly find our updated XOR sum. So we would do this by XORing every element like this. So with our prefix, that would be prefix R, the first R elements. And then we would also XOR with this, which is prefix L minus 1, the first L minus 1 elements, because we don't want to include this. So essentially what we do then is these elements get XORed twice. So that has no effect at all. And then these three elements get XORed once in this segment here. So they get essentially toggled between for XOR A and XOR B. This is exactly what we want. So let me grab my code for this. So here we're just reading in the data, we generate our XOR prefix based on the string of bits we get. We assign each element to either being in the 0 set or the 1 set. We construct our initial XOR sums, and then for each query, if it's a 2 query, we just spit out our current XOR sums. That's easy. And then this is how our update works. This case, I think, is this case is for like if we have if L is at the beginning. So this is L and this is R. We don't need to do this empty segment and then this. We can just do this. So I guess this is actually a little bit unnecessary, but it doesn't matter. So this is what we were talking about. Our current sum gets updated with prefix R, so that's this segment from all the way at the beginning to R, and then L minus 1, which is all the elements prior to our segment, to cancel out the unwanted elements from prefix R. And if it's a type 2 query, we just spit out our answer. So that's it for that problem. Essentially, we XOR our current sums with every element in our segment one time, which is what we want to toggle them, and then every element prior to our segment gets XORed twice, which has no effect. Time it takes is n plus q, since we need to build the prefix XOR array, which takes n time, and then handling each request takes q time. N could be much larger than q, q could be much larger than n. So it's n plus q, and then we need on space to store our prefix XOR array. So moving on to problem F. So in this problem, a key insight I want to start off with is if we have an animal X that we sell, we miss out on some amount of money if we sell it right now, and that amount of money is equal to the sum of the costs of all the animals afraid from X. So let's take the example they gave us. A equals 34413, and then the cost of the animals is 34567. So if we sell animal 4 right now, we miss out on 9 money because this animal will no longer be afraid, this animal will no longer be afraid. So we lose the opportunity to get double price for those if we sell animal 4 first. So at every moment we can keep track of the amount of future loss we'll have by selling each animal at the current moment based on what animals are afraid of it. And our total revenue is bounded by 2 times the sum of this array. So the sum of this array is 15 or 25. So our total revenue is going to be less than 50 because we can't get double price for every single animal, since the last animal will never be afraid at the end, and we can't get double price for it. So for each move, we will greedily pick the animal whose sale will cause us to lose the least revenue in the future. So our first step is to have some sort of table, and for each table we will have its animal ID and its loss, and the loss caused by its sale if we were to sell it immediately. So we'll say 1, 2, 3, 4, 5. These are the indices of the animals, and then if we sell 1 right now, we lose out on the opportunity to get double price for animal 4, so that's 6 lost. Animal 2, there's no animals afraid of 2, so there's no loss associated with that. With 3, we would miss out on this one and this one. We would have 10 loss. For 4, it would be this one and this one, 9 loss. And then for 5, there's no animals afraid of 5, so it's 0. So we would want to sell 2 or 5 first, since it would not lower the price we could get for any other animals later on. And then we would update our table accordingly. So I just demonstrated how to compute the table initially, and the logic behind the updates is this. When we sell animal X was afraid of some animal Y, by definition in the problem. If animal Y has not been sold yet, so we still have it, that means that we can decrease the loss associated with Y's sale by C of X. So let's say we sell 2 first. 2 is afraid of 4, but we don't. That means we can decrease the loss associated with 4 to 5, down to 5. Because if we sold 4 right after 2, we already got double price for animal 2. So we would only miss out on not getting double price for animal 3. So in order to actually implement this, we need some sort of data structure that allows us to do a couple things to this table. We need to quickly be able to find the minimum, whichever the minimum represents the animal with the least loss if we sold it right now. And we also need to be able to update our entries. So we are going to be able to do n find and delete minimum operations, which represents us finding the best animal to sell and then selling it. And we also need to do n updates, where we update the cost of or we update the loss for the animal that the animal we just sold was afraid of. So we need to do n of these operations, and based on the time constraint, 2 seconds, we need to be able to do these operations in log n or faster. Fortunately, by using the data structure set as a priority queue, we can accomplish this. So how the priority queue works is, if we choose, if we populate our priority queue with the loss as the first number in the pair, so 0, 2, 0, 5, 6, 1, 10, 3, 9, 9, 4. Actually, the set will automatically order these for us, so it would actually be I'm fucking stupid. 9, 4, 10, 3. The set keeps them ordered. So if we look at the beginning, we'll always have the animal with the minimum loss. So finding we can do in O of 1. In O of 1, look at start. So we find this in constant time. Delete takes log n. And then we need to update it, right? Because in this, if we sell 2, we need to update 4, because 2 is afraid of 4. Now, we can't actually edit this directly. That's just the way set works. But what we can do is we can delete this. So another delete, log n, and insert is also log n. So 4 carries a loss of 5 now. So we would just insert. So this gets deleted, this gets deleted, and then we would insert 5, 4 in here. So we can do all our operations in log n time. Perfect. We will have to do this up to n times. And that's how we arrive at our n log n runtime, which will be fast enough for this. So if I get my code for this, I keep track of, for each animal, I keep track of which other animals are afraid of it. That allows me to compute the initial loss, for each animal. And then we populate the priority queue with our key value pairs. Then for this loop, we choose PQ begin, so this is the head of the priority queue. This is the animal with the least loss if sold immediately, so we print that out, delete it. This is the animal it was afraid of. We get the key value pair and we search for it in the priority queue. If it's there, which means the animal hasn't been sold yet, then we delete it and then make the update. If it isn't there, so if this iterator points to the end of the priority queue, it means that animal's already been sold, so there's no update that needs to be done. And we do that for each animal in the farm. I only had this loop iterate n-1 times and then spit out the last element when it's the only one in the priority queue, because I think I had something where if I deleted the last element in the set, that caused some sort of error or something. I don't know exactly how that works under the hood, but this was a quick workaround for that. So yeah, O n log n time to perform our n operations on our priority queue, and then on space for our initial map and our priority queue. So last problem, replace with product. So um, we take some segment, one segment in the array, uh, and we take the product of all the elements in that segment, replace the segment with its product, and then take the sum of the array after that. And we want to choose a segment that will give us the greatest sum in the end. So it should be fairly easy to see that if we have a bunch of ones at the start and a bunch of ones at the end, let's say like this, our segment will never be like this. It will always ignore any leading ones and trailing ones. That's because they will not contribute to the product, but they could contribute to the sum. So if we did this, this would become 24. So if we took this as our segment, this would get turned into 24, and then we would get 31. But if we chose this whole thing as our segment, we would still get the same product, 24, but there wouldn't be these ones to contribute to our sum. So I'm going to call we'll call this the preliminary segment. This is our search space, so to speak. We never have to search outside of this. So I'm going to call this SL and SR. So we'll construct a prefix sum array as well as a prefix product array for the array, and also we will mark down any index where the element is not 1. So that would be this one, and this one. And we'll see the use for all of these vectors later. So the first thing I want to prove is that if the total product, our total product can be found with the last element of our, it depends on overflow, but if the total product of the whole array is over 2 of n, this is our answer. And the Codeforces editorial mentions this as well, but they don't give a proof of it. I found a rather intuitive proof in the comments for the contest announcement. So credit to Sole Proprietor on CF. It's his comment that I'm taking this from, where the worst case scenario is we have some array like this. So we'll say it starts with some p greater than 1. The rest of the array is filled with 1s except the last element, which is 2. So the reason why this is the worst case for multiplication is because these two elements could not have a greater collective sum for the product of 2p. Any pair of numbers that adds up to 2p, or product, have a product of 2p, would have a lesser sum than this, which would incentivize us to multiply them if their sum was lower. Because this is the highest possible sum, it incentivizes us to not multiply at all. So if we were to multiply them, we would get 2p as our answer, because we would lose all of these ones when we multiply if we do this, if we take this as our segment. And if we don't do any multiplying, so no matter what the array is, we can always choose not to multiply at all by just taking a segment like this on any number, because then the number doesn't get changed. So if we multiply, we get this, and if we don't multiply, we would get p plus 2 plus n minus 2. And the reason why it's that is because there's n minus 2 in the middle of these, if this whole array is size n. So this answer becomes n plus p. So in order for multiplying to be worth it, this 2p has to be greater than this. So in other words, P has to be greater than N. Because if we subtract P from both sides, we get P greater than N. And this is the worst case. So, and in this case, clearly there's no other. It's either we take this segment, the whole way, or we take one of these, like, essentially empty segments. Those are the only two choices we have. So, the result of this proof is if the total product of the entire array is greater than 2n, then we can just choose these two. Otherwise, we get to the next step, which is if the product is less than 2n, that means there's at most log 2n elements that are greater than 1. If there were, the reason why I can prove that if there were more, then the product would be greater than 2n. So let's say there's more than log 2n elements that are greater than 1. So all of these elements are at least 2. So if I multiply all these together, they're all at least 2 to the power of log 2n. Then, since there's more than these, we would get more than 2n. So if the total product is less than or equal to 2n, that means we have that are greater than 1. So because of what we said at the beginning here, with leading and trailing ones being ignored, if there are, I'll call log 2n k, that means there are at most k endpoints for our segment. Because, let me make some space. If we have, so k equals log 2n, k segment endpoints. This is because if we have some ones here, leading ones, and some trailing ones here, we have four here. It doesn't matter if there are ones in between here or not. It doesn't really matter. We can choose this segment, this segment, this segment, this segment, this segment, or this segment. Those are our only choices. So if we have, or I guess we can also choose each of these segments by themselves. So if we have k endpoints, we have essentially on the order of k choose 2 possible segments. But n, according to the problem statement, is up to 200k. So that means k, which is log 2 of n, has to be less than, I think it's like 19 or something. And we can have 19 on the order of 19 squared segments. So that's less than 400 segments, possible segments. So we can brute force, we can brute force all of these segments. So this is where our prefix sum and product come into play. Because using our prefix sum and product, we can essentially brute force and find the actual result, the actual score of the array, if we chose this segment to be our answer. So if our segment is LR, we would choose, to get the product of L and R, we can do prefix product of R divided by prefix product of L minus 1. So the product of all of these elements minus the product of the, or divided by the product of these elements, is the product of these elements. And then we need to get the sum of this part of the array and this part of the array. So plus prefix sum L minus 1. That's the prefix sum of this. And we need the prefix sum of this plus prefix sum of n minus prefix sum R. So we take the prefix sum of the whole thing minus the prefix sum of this is the sum of this part of the array. And then this is our answer. So we can just compute this for every segment, for every possible segment. Each segment candidate is any ln r such that L is less than or equal to R and AL greater than 1 and AR greater than 1. So any two elements that are not 1 are candidates to be the endpoint of our segments. So if I grab my code for that. I have, these are the indices I keep track of, which are greater than 1 when I read in the data. Prefix product, prefix sum, calculate those. If we ever get past 2n on the product, then we can multiply the segment, our preliminary segment we said, which in this case would be this. So if we do that, like I said, we simply trim out all the leading ones and the trailing ones, and then we have our answer. Otherwise, if the product is less than 2n, then this is where we brute force all the segment possibilities. So we iterate over the indices that have elements that are not 1. So this is our iterate over the left, iterate over the right, calculate what the result would be, and then keep track of the best segment here. And then once we calculate for all the segments, then we just output the best one. So yeah, that's all for this contest. Once again, I will post the link to this document with these notes, and also I will link my submissions in that document as well, my Codeforces submissions, so you can have a look at the code. The last thing for the runtime for G, it takes O of n time to compute our prefix sum and prefix product. If n is large, that will be the dominant part of the time complexity. For smaller n, roughly 40, depending on the numbers, the term where we have to brute force all the segments will actually dominate. So the runtime if n is smaller, it could be log n squared. And of course, we need O of n space to put our prefix sum and prefix products. So yeah, once again, everything will be linked in the description, and hopefully that was helpful.